Everybody, good afternoon. Welcome to our pre-calculus class. I think this is the last class for you all today, I believe. Well, again, happy inauguration day. Some of you, I'm hoping, did see that in advisory or probably still seen it at home as well. Our check-in is pretty straightforward today. In general, how are you doing right now is our check-in. Maybe some of you are tired. Some of you perhaps hungry or stuffed after lunch. Just in general, how you feeling? Or you could, talk about the inauguration if you have any feelings towards that as well. That's going to be our check-in. So I could double check on attendance, everybody. But welcome, y'all. Just in general, how are we doing? How are we feeling? All right, I see a few of us there in the chat. All right, so we have relaxed, feeling hungry, good, feeling stuck, feeling good, feeling a bit overwhelmed. That makes sense. Yeah. As far as me, I'm kind of sleepy. I don't know. I needed a little bit more sleep, but it's on me because I sleep. I slept at midnight, but I did have 7 hours, but I'm still sleepy. If I slept by 10, I could probably be pretty good. All right. Feeling a bit tired. Okay. Feeling all right. Just feeling a bit neutral. I feel I've been having a great week. That's awesome. Some great positivity there. All right. Again, if you also just came in, please make sure you answer the check-in question so I could, get you in. I don't accidentally mark you absent. That would be great. I'll try to announce who I'm missing though, so that we get everybody. All right. Oh, we got a few more. All right. I'm feeling a bit tired, and I feel okay. Yeah, those are all very valid. All right. So this is who I'm missing, everybody. According to our check-in, according to who I tried my best to look through who we have. So I'm missing Kalia, Justin, Rainy, Kevin, Jose, Jonathan, Amara, and Sakaya. So that's who I'm missing. Oh, we do got Kevin. My bad, Kevin. Let me go ahead and fix that. There we go. You're here. Don't worry, I haven't entered it, so don't worry. All right, let me go ahead one more time. Kalia, Justin, Rainy, Jose, Jonathan, Amara, and Sakaya. That's who I'm missing. So if we're friends with them, if you could please send them a text. Other than that, I'm going to go ahead and enter our attendance so we could get a move on with what we're doing today. Okay, thank you. So if someone's on their way, don't worry. I'll make sure I update that. I have my Power School open. All right, y'all. So here's our agenda. Again, I just posted these slides. So you do have access to these on Google Classroom. Um, I just took attendance. We're going to revise an answer. So we kind of started this activity yesterday or the day before. It was yesterday. And we're going to actually continue with that problem. We're going we're going to try to improve our justification. After that, we're going to move on to our next topic that we're going to talk about. We're going to investigate how fast a ball is moving, how it's going, and then we have a checkout. So asynchronous number 6 is posted. This one is due on Thursday. And I did send some emails if I'm missing any prior asynchronous work. Again, just let me know when you could get those in. And if you're having any struggles with them, just jump into my office hours. I'm happy to work on them with you one-on-one. Let me know if anyone has any questions about our agenda on the async work or anything like that. Okay, No problem. Thank you. All right. And for those that just came in, again, please let me know. Send me a private message so I could go ahead and fix up the attendance. I did hear like two of you come in. Let me know. All right, everybody, let's jump into our back into the activity we started the other day. Again, you definitely, I'm going to be entering the credit for this activity today. So you definitely want to make sure that you're following along with us, following the instructions. If there's a part where you need to come in and comment or fill out a Google form, you want to make sure that you jump on that train. All right. Okay, so again, as a refresher, here was the activity we started the other day. So I'm going to debrief asynchronous number 3, and you all actually did similarities and differences already on that. If you were absent, I mean, you have access to these slides. You're able to click on the links. And the goal with the activity was what makes good math justification. That was our focus. Then after we're done with our kind of little discussion about the similarities and differences that we saw with the student work, you all are going to have a chance to revise a student response using Google Form. That's going to take about like 8 minutes on Google Form. Then after this activity, we're going to transition into our next topic for this unit that we're in. So again, the reason for this, why this exercise, this activity right here is designed to help improve your justification. That's actually our focus for this module. And something you need to think about while we're looking at the student work is what makes a good math response. All right, so the problem that we started looking at yesterday was asynchronous number 3. It was basically on asynchronous number 3, the first 4 problems, but our focus was on how students were justifying number 4. Does Brenda catch the ball? Why or why not? Let me give you a moment to go ahead and just refresh yourself on what we looked at yesterday. So let me give you a few seconds here. Okay. And I know yesterday I gave you all a minute to take a look at this as well. Let me go ahead and show you where we left off yesterday. So we're period 3, and you were asked to find some similarities and differences between two pieces of student work. Let me go ahead and put this back into the chat so y'all can review what you wrote. Or if you didn't get to write anything, right, you want to go ahead and write your response. So go ahead and open that document up and just go ahead and refresh ourselves on what we wrote, what we saw. You definitely want to refresh here. What were the similarities and differences when it came to question number 4? And again, you were trying to answer samples use justification. Good, I see 4 of us back on this document. Maybe you could go down and just refresh yourself on what you said. Here we had a variety of different responses on similarities and differences, and or how each student used justification. So let me wait for everyone to go ahead and get on this doc, because you definitely want to refresh yourself first on what we did the other day. Great, we got 7. Let's wait for all of us to get on here. The link is in the chat. I'm gonna put the link back in just in case you need it once more. Here's the link. And again, we were looking at question number 4. We're trying to figure out whether or not Brenda, who's at the coordinate point 3,6, will catch the ball, given that the ball has this table for its motion. If you take a look there. Great, we got 14 of you in. And again, if you did not get to answer this, go ahead and start typing your answer in. I'll be taking a look at this and adding in credit for this participation today. Otherwise, go ahead and take a look at what everyone else was saying, as far as their thoughts when it comes to how these two samples use justification. Again, I saw similarities and many of us saying like, oh, sample 1 explained it better, but then sample 2 was kind of like used more concrete math. Like sample 2, like they got the 0.20 from their math reasoning, and sample 1 kind of was referencing the big idea of a limit. So it's kind of like which student will we say kind of justified better? All right, so let me give you a moment to refresh here. Refresh and or add a response if you haven't yet. I'll let you do that. Give a moment for that.
My computer's on 2%. Bear with me.
Okay, try to find the charger. If not, let me know how I could work with you, Jaleel. So it's okay if you have to log out and come back in as well. All right, y'all. So I'm hoping y'all had a chance to refresh what you wrote, or maybe you had some time to actually respond to this now. And I just want to say, so both of these, some of you noticed that both of these two samples said that the limit does not exist. So this one says the limit does not exist might since there might be that the left and the right do not meet up if they were placed on the graph. And this one says does not exist because the limit should be 6, not 6.20. So this person thought the limit was 6.20, but that it should be 6 in order for the limit to exist. So let me go ahead and tell you all something. So actually both of these samples are incorrect. So actually the limit does exist in this case. If the limit were to not exist, that is to say that that ball just disappears out of thin air and kind of just reappears. So because this is a ball in motion, the ball kind of has to have these points filled out. And you kind of have to reason with it, like where would the ball be during these times? And you're going to be using the limit to kind of show where the ball would be at. So that's just the thing. I purposely chose two samples that were incorrect, but it didn't matter here because what I wanted you all to focus on is how these two were justifying their work. You could literally have a proficient justification even if the math work is inaccurate. So let's go ahead and talk about this. So we could get off this document. Let's X this out. And I'm gonna jump into our debrief, everybody. So I'm back in our slides. Let's talk about it. So again, you have these copies of your own, right? You just go to Google Classroom and open up your own copy. Remember, we're not taking notes anymore in this class. The expectation is you just open up your own copy and you annotate the slide as we talk about it. And that's going to be basically how you're taking notes now. Okay, so um, first off, can I tell you all something? So when I first did this problem, I actually said the answer to the limit is 6. So I actually got this problem wrong. I did this really quickly and I didn't really think about it until you all started working on it. And I saw a lot of 6.2s coming up as the limit. And I basically changed my mind because I agreed with the justification that those students had. So let's debrief this. So yeah, just telling you I got this wrong and this is okay because it's a process of learning. All right, so the positional motion of the ball, we know it cannot have any gaps or breaks. We know that that ball needs to keep going in motion. It would not make sense that the ball just disappears somehow and then reappears. So we know that it can't be that this table is blank, first off. So why we're using limits is because we can predict the ball's eventual position. We can approximate where it's going to be at by using limits. And this is how we're applying limits to the real world. Like we know that ball is going to be going somewhere. It can't just blank out in the table like that. But we use limits to make an approximation. So super important there. Why do we need limits here? Next one. Okay, so actually, according to the information given, a lot of you were saying that the limit was either 6 or 6.2 actually in the work that I seen. According to the information given, I changed my answer. I said 6.2. It appears that the limit from both sides is approaching 6.2. So let me go ahead and kind of go into why it's 6.2. And that's what like student sample number 2 said. So let me use my little annotation tool. All right, so notice first off that on the X, these values are very closely approaching 3 from the left-hand side. Those are numbers less than 3. Let me change my color. Left-hand side, they're trying to approach X equals 3, and 3 represents seconds. And on the right-hand side, we are approaching 3 from the right. And this is just like right after, like at 3.001 seconds. So it's a number really close to 3. Now, this problem purposely put ... there so that you could kind of make an estimation based on where you think the ball could be at using limits. Now, if we go on the Y, the side over here on the Y, we're again need to make sure that we're checking like where's the limit or where's the Y value going to as it's approaching X equals 3 from the left and the right. So I see that this is 6.228, 6.210, 6.202. Now, because it stops there, we have to just make a generalization. So I would say that the limit as this is approaching 3 from the left is going to be 6.2. I can't say it was 6. I can't just kind of infer that it's going to be 6. So that's why I agree that on this side it's going to be 6.2. Notice that you need to make sure you check the other side. So now coming in from the right, I notice that these numbers are also approaching 6.2. This is 5.9, 6.14, 6.198. I could definitely say that these are kind of approaching 6.2. Another reason why this would not be 6 is 6 is actually over here. 6 is between 5.9 and 6.14. So it kind of wouldn't make sense that it's 6 here and somehow the ball goes at a higher height. It kind of has to go back down. So the limit here is going to be 6.2. And that's the reasoning for that. Let me pause to see if anyone has questions about why the answer to the limit is 6.2. And this is according to the table. This is not related to where Brenda's at all. This is just like, where is the ball at 3 seconds? And according to using limits, the ball at 3 seconds is going to be at 6.2 feet. It was feet, so let's make sure we add our units. Let me pause here, see if there's any questions, and then we're going to talk about whether or not Brenda will catch the ball. Okay, there's no questions. I mean, feel free if it comes up. Let's continue to debrief this. Okay. So great, the limit is 6.2. So that means we can make a prediction that the ball is going to be 6.2 feet at X equals 3 seconds. Next thing. So originally, when you look back at the original problem, it says that if Brenda jumps high enough, she's able to catch the ball at 3.6. So 3.6 must be the position that Brenda's at. So at 3 seconds of the ball's motion, she can jump high enough to reach 6 feet. So what I did is I made an additional model. So I went on Desmos, and first off, I tried to plot the points. So I plotted the points here in green. These are the points that are found in the table. And in black right here is Brenda's position. So sorry, that's how high Brenda can jump. This right here is 3.6. So this is the ball's motion. Down here is Brenda's position. And let me show you what that looks like on Desmos and how I kind of put that together. Not opening. But there we go. So basically, I just took the table that was given to me and I graphed it. And 3.6 was where they said was how high Brenda could jump. So I want you to notice that This is where Brenda's at, and this is where the ball is at. And the only difference between Brenda and the ball is by like 0.2 feet, which is basically like 2 inches or a little less than 2 inches or so. Um, and you're going to reason whether or not she catches the ball. So again, this kind of helps me see, okay, if Brenda can jump this high, it kind of leaves this problem open-ended because 2 inches could be her extending her arm. So some of you said she will not catch the ball because she's 0.20 off. But what if she just extends her arm 2 inches and she's able to catch the ball? Because this is actually a very short distance. We're just very much zoomed in. So what that means is that this problem actually allows for open-ended answers. One can argue that she catches the ball or not. It actually depends on your justification. So you can argue that she catches it or not. It depends how you're using the evidence from a graph, a table to kind of make your reasoning. Here's some common pitfalls that I saw when I was looking at y'all's work. Number one, some thought that if Brenda didn't catch the ball, it meant the limit doesn't exist. So that is incorrect, right? You check whether a limit exists by checking the table. You check whether the left-hand limit equals the right-hand limit. In this case, the limit does exist, y'all, because it's approaching 6.2 from the left side and the right side. So the limit does exist, and that does not depend on whether or not Brenda catches the ball. So that's a super important common pitfall I saw in the homework. The next common pitfall was some assumed that the answer was 6 or that the limit was 6 because some assumed that Brenda has to catch the ball. So they forced this middle number to be 6. And I want to admit that that's something I did. It's like I wanted her to catch the ball. So I wanted the ball to be at 3,6 where Brenda was at. So those were some common pitfalls. That your limit table represents the ball's motion. And that dot right there represents Brenda's position. You're gonna have to separate them. And it does not rely on whether or not Brenda catches the ball when you're trying to argue whether a limit exists. You wanna go back to your facts and what evidence you have. So let me know, does anyone have any questions about the debrief right now? So again, you can argue that she catches the ball or not. It actually, you can be right in either case, depends on how you're gonna justify this. Okay, I have to catch my breath. Sorry guys, I talked too fast. All right, cool. So we don't have questions. I'm hoping we're ready for the revisions, everybody. So what I mean by revisions is I'm gonna give you a Google form. You're gonna be seeing a piece of student work and you're gonna try to revise their answer to improve their justification. But before you do that, I'm gonna tell you what does good justification look like. So again, this is an open-ended problem. You could say Brenda catches the ball if you justify it correctly, or you could argue that Brenda does not catch the ball. Again, if you justify it correctly. Or you could even say the likelihood of her catching the ball is, likely or so. Depends on how you reason it. So again, the focus on this is justification, not so much the correct answer. Because in the real world, you can make bets that somebody was likely to catch a ball, but sometimes things go wrong, right? They trip, they fall. Sometimes math itself won't help you make that prediction. All right. So according to me, when I'm looking at your work, what does good math justification look like? It looks like this. Here's some bullet points. So first off, you want to interpret, analyze the problem. And I saw both of those student samples doing that. They both dug into it and dug into the math, and they were trying to reason whether or not Brenda caught the ball. You want to definitely reference mathematical models or create models. Um, so the thing that I did when I went on Desmos, I just tried to graph it to kind of see like where's Brenda, where's the ball. I did this second part. I created like a new model. Yes, they gave me a table, but I kind of went on Desmos to kind of create something new that will help me visualize what's happening. Or you're going to reference your table or you're going to reference any other model that's given to you. Good math justification uses those as references. So for example, student sample 2, use that the point 20 part. She was referencing, or she or he was referencing the math, right? So they're referencing the math work, which was a good one too. Um, the other one cites evidence from context. So context means you're citing evidence from the real world situation. Again, those of you who are saying like, oh, the answer is going to be 6 because Brenda has to catch the ball. Again, that's not going to be evidence from context because that's making an assumption. And that's what I did too. So you want to make sure that you're citing your evidence from the correct scenario that we're looking at. And lastly, you want to apply the big idea. So I think student sample 1 did this really well when they were mentioning the limit. But I would say that both student samples that I was looking at, I would say they're developing. They're developing and they both need a little bit of more push to improve the justification. Let's see what's in the chat. Well, it's okay. So just try your best. And it's okay if this is a struggle. So this is just look fors. And we're just going to continue to work on this and try to improve it. And it's all right. And also, by the way, y'all, I do have office hours right after this, and I'm happy to work with anybody one-on-one. We could talk about this problem or any upcoming, asynchronous work that you have going on. Let me know. Again, this is not going to be graded on accuracy right now. This is just based on us getting some good practice. So this is the revision time. So let me go ahead and give you the link, and we're going to have about 8 minutes to get this done. I'm going to first, of course, open it with you, talk about it with you, and then y'all can get started. Again, do not worry about getting 100% right or nothing like that. Let me click this with you. Okay. So when you open up this form, you're going to be asked for your email address. Definitely need that so I can know who's I'm grading or looking at. And grading, it means I'm going to be grading on just participation for this. So don't worry about grading on proficiency. I'm not going to be grading on proficiency. Number 1 asks you, so here's the sample response for number 4. It says, what feedback would you give the response to meet the criteria for good math justification? And remember, the criteria for good math justification is on slide number 8 for today's slides. Again, our slides are on Google Classroom. So for today's slides, slide number 8, this is what good math justification looks like. So you're going to read the response, and you're going to answer by offering what kind of feedback you would give this student to improve their justification. After you think about some good feedback to give the student, number 2 is you're going to now take their response and you're going to try your best to revise and improve it, trying to use the best that you can, a good justification response, whether or not Brenda catches the ball. And that's going to be what we're going to be doing right here for revision. Yeah, so right here, let me go ahead and put the link right back in. Sorry. Making sure everybody has the link. What you're revising is right here on the form, on the Google form. Let me know if anyone has any questions. So we just talked about this problem. We debriefed it. I gave you guys a little bit of common pitfalls, right? Then I went over what makes good math justification. That's the next thing. It's all here. Then you're going to go ahead and look at a response. You're going to offer feedback. After that, you're going to try your best to improve their response by trying to add in the bullet points of what's good math justification. So that's what you're going to try to do for this Google form. So this is accessible to anybody, even if you're still a little bit lost on what we're doing right now. So that's just a little side thing there. Does anyone have any questions though, before I start the timer and we get all started on this? So again, this is going to be graded on participation. So don't worry about the accuracy of it. Just try your best on it. Okay, I'll be here if anyone has any questions, all right? I'm going to also be checking in to see how much more time we need, but I'll give us 8 minutes. We'll check in, and then we'll move on from there. I'll be here, everyone. Let me let y'all take your this little Google form. Again, try your best. Do not stress over being right. It's not about being right. Remember that. I got this problem wrong initially, so it's not about that. It's about learning and doing your best. All right, y'all. 8 minutes. Again, private message me for any issues or concerns. All right, hey everybody. So I see that we have 10 responses in. I'm gonna go ahead and give us 3 more minutes on this, and then we're gonna come together, move on to the next thing. Again, let's do 3 more minutes. All right, everybody, welcome back. So just make sure before our class ends that you go ahead and submit this. Thank you so much for giving your thoughts on the revision. And also thank you so much for those who are still like, stuck and learning how to do this, who still did the form, right? You're putting in your questions and so forth. That's perfectly acceptable. Awesome. Let's go ahead and transition into the next thing that we're going to be learning about that's going to help prepare us for the actual mini finals where we're going to, actually put this stuff into practice. But let's get some learning in before that. So here are some things for our next train of thought. Some essential questions for y'all to think about are: how can I determine how fast an object is going at an exact instance? And how is the slope of a function connected to speed? So those are the two questions to just think about in your mind as we're going into this new lesson here, part of our unit. Again, it's not like super new because we're going to still be kind of playing around with the idea of limits and how we're using them in the real world. All right, let me give you all some time to like read this slide. Remember, y'all, we're not copying down notes. We are making our own copy of the slide and just following along and or annotating, whatever helps you follow along the best that you can. So let me leave this slide up here for a moment. All right, let's go ahead and transition into the activity. Now, this is going to be interactive notes. Again, you're not writing down notes, but you're engaging with the notes that I have with you here. And how we're going to be doing this is on a single Padlet. So instead of me like coming up with different Padlets, it's actually going to be a single one with all the questions on there. All right, so this is our first one. So this is like an entry question. So this is super open. Again, for your participation, either put your initial or your name, right? If you're uncomfortable with either initials or name, just send me a text and remind, let me know what name you rather go by. But this is what I want you to think about right now. So imagine, so again, we're looking at balls being thrown, just like Brenda's problem, but imagine you have a ball that's thrown. So, and you want to figure out how fast it's going. What can we do? So this right here, this line, the kind of like an upside down parabola, is representing the ball's motion or its projectile in space. And I just clicked on two random dots on the graph here. And your goal is, okay, so I know that over time in seconds is on the x-axis and the height of the ball in meters is y-axis. So given this information, what would you do or what ideas would you have in order to kind of determine how fast the ball is going? So that's going to be our first question. And we're not using the chat, we're using a Padlet. Let me give you all the Padlet, period 3. Oops. Here's our Padlet, and I'll be joining the Padlet with you all in a second. Let's put this there. The link to the Padlet is in the chat, and I'll go ahead and click it with you. And again, we're going to start this lesson. We're not going to be able to finish it until our next time that we meet, right? But this is what the Padlet looks like, and we're on opener question number 1. So again, this is the problem. Imagine you have a ball thrown and you want to figure out how fast it's going. What are some ideas? What can we do? And use this as an example. The ball being thrown, the height that it's at is in meters, the time is in seconds. And how you're going to add a post is you just click on this plus here. If your name is not popping up at the top, you're just going to go ahead and make sure maybe for the title, put your name or initial. Does anyone have any questions before y'all are starting with this? Let me also make sure you all can, yeah, you can write. All right, awesome. So I see that some of us are already getting started. Again, this is part 2 of our credit today. So we had our Google form, that's awesome, but let's jump into this Padlet and interact with the ideas that you want to think about before we actually know how to do all this. I'm going to put the directions again in the chat. Let's have a few more seconds on that first opener question, number one. Again, make sure you put your name or initial. I want to make sure we capture everyone's thoughts and that we're all on there for participation as well. All right, I'm going to go ahead and start pointing out some ideas that some of y'all had. Again, you want to make sure that if you want to make sure you put in your comment there for the first column. Let me know if anyone's having any trouble with that. But a lot of you are saying find the average rate of change using slope. I see divided by time. And yeah, well, like when you're making the slope formula, you do divide by time, distance over time. So that's another way of, doing average rate of change. Ooh, somebody's making a reference to the big idea number 5. That's superb. Yep, thank you. Thank you for the time check, Julia. I got it. Um, good. So slope and rate. Yeah, slope is going to be synonymous with rate, especially when you're dealing with real world situations. We're not just talking about slope, we're talking about a rate, which is like speed or velocity. Oh, I love this because this person for Shirley, so looked at the big ideas packet. Draw a secant line. Be able to use the slope equation to calculate the average rate of change. That's right. Awesome. And then there's somebody who put find the slope. They're anonymous. Again, make sure you comment, or you could add a little comment here of your name, or just edit your comment to make sure you get your credit. Again, there's another one. Dividing my time. Divide the time. All right. Awesome, y'all. Let's go ahead and transition into the next part. So again, this is the introduction to this activity. So in the next part, I'm going to review with you. Y'all were right. Everyone has said slope, average rate of change. Yes, that's correct. And in this next slide, all I'm going to do is just review with you all how to exactly find the average rate of change and how that's later going to relate to instantaneous, but don't worry about that just yet. So you can find the average rate of change between any 2 points and to determine velocity or speed. And the line that connects these 2 points, yeah, it's called the secant line. So let's say I'm trying to find the slope between x equals 1 second and 2 seconds. So between those 2 seconds of the ball being thrown, let's find the average speed. So remember, y'all, we don't have to copy this down. You have a copy of these slides with you. So you're just opening on your own and taking a look with me. So again, here is our handy dandy slope formula that we're so used to seeing throughout our math years. But it's a very powerful formula, y'all. So notice all I had to do was do the change in y over the change in x. You could, if you want, if it helps you, label your points. So for example, let's see, which one did I make x1 and y2? So my 9 looks like, so it looks like I made this one x1, y1, and then x2, y2. Let's see if that's how I set it up. So we have, nope, I did it the other way. Sorry, y'all. It's because I want to make sure I correlate with how I wrote it. And actually wouldn't matter which points you label, x1, y1, or whatever. I'm pretty sure that was correct, actually. So y2 is going to be 6. So then this is x2. That was right. So y2 minus y1, so 6 minus 9, all over 2 minus 1. There we go. Just making sure I kind of labeled my points. You still will get the same answer if you did this one x2, y2, and this one x1, y1. You'll see. The only thing is you'll be dealing with negatives though. All right, so I set up my slope. Let's calculate that. I got as my answer, so 6 minus 9 is -3. 2 minus 1 is 1. -3 divided by 1 is just -3. And don't forget your units, especially when we're dealing with real world stuff. Because this was a ball and its height is in meters and time is in seconds, its rate is going to be meters per second. So that's m, and this should be like a little division sign. So meters per second. That is the average rate of change of the ball between 1 and 2 seconds. Another way you could think of this is the velocity of the ball. And it's negative because the ball is going downward. So it makes sense that the rate is negative here. So just make sure you let that sink in. It's going to be negative because the ball is going downwards from this point to this point. It's sloping down negatively. So this is going to be a negative velocity. If you want speed, all you have to do is make this number positive. So the speed of the ball, speed is never negative. Speed of the ball would be just 3 meters per second if you're talking about speed. Because notice when you're driving a car, you don't go no negative speed. Your speed is just your speed. It's always going to be positive. But in this case, velocity can be negative. So just a little side note on that one. All right, let me know if anyone has any questions. I know I give a Khan Academy practice on reviewing how to do average rates of change. So it looks like we're gonna go ahead and pause here, everybody, because we're actually out of time. So we're gonna be returning to this lesson the next time we meet up. And I hope you all enjoy Inauguration Day. So far, no drama today, what I hear. So don't worry about our checkout question, everyone. I do have office hours right after this class, so feel free to stay back if you have any questions. Otherwise, y'all have a great day. Bye, everybody. Enjoy today. See
Have
ya.
a good day.
Bye. Take care. Bye, y'all.
Bye. Bye. Take care.
Bye. Take care as well. Bye, y'all. All right, so I'm going to go ahead and transition into office hours. So if you're here, I'm happy to help you all with some office hours.
Miss Sedano?
Yes.
Oh, I got a question because I forgot to tell you an advisory because I just saw it right now.
Mhm.
What do I do? Like, okay, so I got admitted to this one college.
Mhm.
So I just want to know what's the next step. Do I have to like go to the website and like?
Okay, did you make the portal yet?
Yeah, I made the portal.
Okay, so if you do have any clarifying steps on that, so perfect, because right now from 2 to 3, Carla has her office hours, by the way. So from 2 to 3, Carla has some. Oh, I'm sorry.
Oh,
No, she don't. No, she don't. She has them tomorrow. My bad. Tomorrow she has them. So
all right, tomorrow.
now, you said you made your portal.
Yeah, I made my portal because also like I don't know. I don't think I put yes to be like on. I don't know if I put like to apply for housing over there, like and like the student. I don't know like how it works because I don't know if it's gonna be online or it's gonna be like
Right.
online.
Yeah, it's gonna depend. So it might be online or it could be in person. But so when you're on your portal, does it show anything in your to-do list or anything like
I
that?
haven't checked it right now. I was just asking.
Yeah, so definitely the next step then for you is to check it. And if you do see there's something in your to-do list, you're going to tomorrow join Carla's office hours and she could help you like one-on-one with that. But yeah, the
Oh,
next step is
all right.
check your portal. Yeah.
All right.
All
Thank
right.
you.
You're welcome. I'll see you,
Bye.
Fabiano. All right. And then Semia and Kalia, do y'all have any questions for me? Let me know if y'all have questions. I'm here in my office hours. I'm gonna go ahead and reopen it, y'all, so that I could upload this recording. I'm gonna reopen my meeting, y'all. So for office hours, if you're interested, just jump back in. Give me a second.